start. We begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for your students, and I just pray you be with us today. Help us to glorify you, what we do. And we pray, Lord Jesus. Amen. So I wanted to just spend a few minutes, and this could be a lecture in linear algebra. I don't know if I'm really going to connect much what we've done this semester, but I just want to talk about the Jordan form and what it looks like. All right. So, and what you can do with it a little bit. So here, I'm mostly thinking about over the field of the reals or the complexes, but of course, you could think about more than that, as we've seen. So the real Jordan form looks like this. Well, excuse me, the just Jordan form. So Jordan form is something like A equals to, say, I guess I need some language here. JI1 lambda 1 direct sum JI2 lambda 2 direct sum direct sum JI let's say S lambda S. So a matrix is in Jordan form if it's the direct sum of Jordan blocks, right? Each one of these blocks is connected, if you will, to a, you could say a Jordan chain, you could say a chain of generalized eigenvectors of length. In this case, I sub I. Oh, tell you what, I sub j. There we go. So, in particular, you'd have this. You'd have A minus lambda j times, let's say, V, I guess ij, for lack of a better notation, comma 1, equals to 0. This is awful, but it's the there's the identity matrix, and then A minus lambda j times I V I sub j comma 2. This is truly an awful notation. 2 equal to V I j comma 1. I can't stand it, guys. So this is A minus lambda j. Let me do it this way. V I1 1 equal to 0. A minus, and when I write a number times a vector like this, I mean, I guess fine, identity matrix, right? Vi2 equal to V. I'm relabeling it because the comma just ain't making it for me here. And finally, A minus lambda j I Vi. I'm sorry, these are all supposed to be I1. Yeah. I'm sorry, not I1, what? I'll get it right eventually. What do I want to put there? Yeah, I'm trying to do this for the jth one because I'm an idiot. You already knew that. Let's see here. You guys okay with me using red? Just checking. It makes you angry? It's okay. I still like you when you're angry. Let's see here. Oh, you're always angry? Hey, nice update. Let's see here. How appropriate. Oh, man. Son of a motherless goat. I will eventually, and see, Daniel, this is why you have to do the the labeling for that problem. Okay. So actually, the length of the chain is the subindex here. So this would be like I sub j is the last one. So like, what I'm saying is I should have done like J1 here, J2, and so forth. I'm sorry.
Wasn't there just I?
Did I still have a residual? Where is it?
Because we have just like base of 1, base of 2, and then at the end we have sub I, sub j.
That's because that's how many there are of it. So, so the point is the basis here. Let's see here. Well, tell you what. Let me just take a step back here. Instead of saying this is A, let's suppose that this is the matrix of T with respect to the beta basis. Yeah. That says that this is this, which means that beta is a Jordan basis. It's really what I'm trying to describe to you is what is a Jordan basis. A Jordan basis is a basis which is formed from concatenating Jordan chains. All right, so like I should start with you know, my current nomenclature, V11, V12, dot 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 dot, V1. How many are there? There's I1 things in that. And then we go V2, 1, V22, dot 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 dot. I think this will clear it up. And then V2, there's I2 of those guys. And so forth and so on until we get to the last block, which would be VS1, VS2, dot dot dot, VS I sub S. This basis is formed from Jordan chains.
This is, you just said the Jordan basis.
Yeah, this is the Jordan basis, yeah. Beta is the Jordan basis for T, right? Now, if I mean these conditions on the I called this matrix A, right? So if you translate, what do these conditions look like? For the linear transformation, these mean that T, right? T minus lambda j. And I'm sorry, these are still wrong, aren't they? So sorry. Well, yeah, let me fix it this way. Sorry, guys. This is easily fixed, though. If you're taking notes in pen, I just taught you a lesson, didn't I? The point is, V is...
Is the superscript for like a column?
What? But I don't, this is the abstract basis. So A, so like, sorry about that. So in terms of, you know, let's say beta tilde, I would do E1, E2, dot, 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 E I1, E I1 plus 1, dot, 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 E I1 plus I2, comma, EI1 plus I2 plus 1, dot, 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 EI1 plus I2 plus I3, dot, 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 e to the I1 plus I2 plus, dot, 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 plus IS. I mean, that's, well, this is the standard basis. Standard basis for F to the, yeah. Well, I1 plus I2 plus da 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 plus I sub S. Now, so let me just again try to unwrap what this is meaning for you, just to make sure we understand each other. When we look at this, this tells us that T of V1j is equal to what? It's equal to lambda j, right? V1j. Just that, right? This says that T of V2j is lambda sub j of V2j plus what? Plus V1j, right? And this, and finally, and so forth and so on until this one gives us that T of V, where was I? V sub ij, upper j, is equal to lambda sub j, V sub ij, upper j, plus V sub I sub j minus 1, upper j. Yeah? So what this means, though, I mean, by the way, if the matrix has this form, what's that say? That says that if we let let's let W W, how about sub j? Yeah, equal to the span over whatever field we're working. I mean, mostly I'm thinking reals are complex. Of I need a label for, you know, like this one. Let's say this is what? I think that should be what? Beta 1, right? This is beta 2, and so forth, right? If you don't mind. So let's let Wj be the span of beta sub j, right? Or if you want me to be explicit, that's the span of, in my current nomenclature, V upper j, lower I equals 1 to I equals to I sub j. What is it?
Is that the jth row or the jth column?
Neither. I mean, these are relations about, these are going to tell us about columns. That's what I'm trying to get to here. But we're not quite there yet. So my point to you is just this. If the matrix of a linear transformation has this kind of decomposition, that means that the subspaces are invariant subspaces. Like this means that if you were to expand it in detail, it's like block diagonal with zeros most places. So in particular, this means if we look at T of Wj, it's a subspace of Wj. So W sub j is what's called T invariant, right? Or T stable in the language, I think, of thumb and foot, right? I mean, this is all implicit within me telling you that that's the Jordan form to start with for the matrix, for the transformation. It says that there are that the subspaces paired to those blocks are invariant subspaces. And so what that also means is that you can define T sub Wj like this as a mapping from Wj to Wj, right? It's kind of some sort of admixture of the restriction to the subspace, but it's not just that, because I'm also swapping out the codomain for the subspace as well. That makes sense only because this is an invariant subspace. And so for this related linear transformation, I mean, how's this defined? It's really kind of silly. If I write it down, you'd be like, yeah, so this is equal to T of x. For all x and Wj, you know, that's the, yay, big deal. But what makes this interesting, of course, is that if we look at the matrix of this, what is it? With respect to the beta j basis. Right, this is that Jordan block. This is that j sub ij of lambda j in my current notation, which looks like specifically, and we can see what I'm about to write in red because of the red equations. See, because the first column in here, right, should be, it should be T of, oh, why have I agreed to talk about this in this notation? I don't know what's wrong with me. D of V1j, it's the beta j coordinate vector of that, right? That's the first column. That's how we calculate and then eventually we get over to the I sub j column in here, and we calculate the coordinate vectors of that. But the thing is, what is that? Well, the first thing right here, right, makes this what? Lambda j, 0, 0, all many, every zeros you need, right? What are the coordinates? So Leah, can you tell me what are the coordinates of this one here? If I calculate the coordinates with respect to the beta j basis, like what is the coordinate vector of this?
Minus of j plus 1.
So like in beta sub j, right? It's an ordered list. It starts with the first thing being v1j. The second thing is v2j, and so forth. So what's the coordinate vector of that? With exactly. So you see, we're starting to create the. You see how that's related to the block we defined last time. And so the story goes until eventually you get to 0, 0, da 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 da, 0, 1, lambda j, right? So that's why the Jordan chains have to satisfy conditions like I wrote in red, because that's just the linear transformation version of saying it has these Jordan blocks. These are the same thing, just filtered through the concepts here. Now, so any questions before I try to say something more?
So wait, for finding the Jordan basis again, I'm trying to remember this. We explicitly calculate like that basis, the original beta, from like the calculations above. We're not already given those, right? That's how we get.
Well, I am just supposing we're given a Jordan basis, and then what does it look like? How's it related?
How do we calculate?
How do you actually find a Jordan basis?
Yeah.
Yeah, that's first we have to be given a linear transformation, right? And then the question is, how do you find a Jordan basis? Is your question? Okay, yeah, we can talk about that.
I know like calculus and
Yeah. So just before I do that, though, one other thing I can say here that's important to say is, if you can talk about the Jordan basis for linear transformation in terms of this abstract basis, right? But once you have a Jordan form, all right, if the matrix is in Jordan form, then the standard basis is a Jordan basis. So that beta tilde would be, these are just the usual standard basis, those actually would form a Jordan basis with respect to this matrix. Let me show you that with numbers. It'll make more sense. So if we have something like A equals to 3, 3, 3, 1, 1, 2, 2, 1, 2, 2, 1, like this, right? That's a Jordan form. And you see, I can calculate that A minus 3i times E1 is 0. I can calculate that A minus 3i times E2 is E1. I can calculate that A minus 3i times E3 is E2. Because, by the way, A minus 3i is what? Using block notation, and then, well, I guess I'm still, I mean, duh. I was already using block notation, wasn't I? Not really telling you anything surprising. So when I take E1, multiply it by this matrix, the first column is just zeros. If I take A minus 3I times E2, the second column is E1. A minus 3I times E3 gives me E2. And this pattern would continue if I had more in the first block, right? So that makes E1, E2, E3 Jordan chain, length 3 with eigenvalue 3. If you want a generator, you could also look at this as E3, well, this is equal to the span of A minus 3I to the power k acting on E3. So this is actually, it is what you'd think of as a sort of a quote-unquote t-cyclic basis. But it's a little bit disguised here, right? Because the t, quote-unquote, I'm talking about, I said t-cyclic basis, but here I mean the t is L sub A minus 3I. So with respect to that linear transformation, if I feed it E3, right? Well, I start with E3, then I take t of E3, that gives me E2. I take t of E3, that gives me E1, right? And so this actually is like one of those cyclic basis pieces we looked at in Dummett and Foote. But it's a little bit disconnected from the transformation. It's like, I mean, this is the matrix of L sub A, right? So it's not cyclic with respect to L sub A. It's cyclic with respect to A minus 3I. It's a little bit removed from that direct notion of cyclicity. But anyway, enough about that. Now I'm trying not to talk about Dummett and Foote. Sorry about that. So for 2, we have A minus 2I. This is the fourth one. It's an eigenvector. A minus 2I E5 is E4. And we also have A minus 2I E6 is 0, and A minus 2I E7 is E6. These are...
But it's not necessarily the case that... Wait. Okay, that's what it's in my mind.
So this is a 2-chain for lambda equals to 2. This is also a 2-chain for lambda equals to 2. These are, of course, our distinct 2 chains. Yeah?
What would the characteristic polynomial for this be?
Characteristic polynomial for this would be x minus 3 cubed times x minus 2 to the fourth. The minimal polynomial here would be x minus 3 squared times x minus 2 squared. Because I only need one copy of x minus 2 squared to knock out both of these blocks. If I do this, then the minimum polynomial is the characteristic polynomial. Because I'd need an x minus 2 to the fourth to kill that piece. Yeah?
What power did you say for the x minus 3, the minimal polynomial?
You said 2, but
Did I say 2? I meant 3. Oh, no. Cubed.
Okay.
Cubed. I'm sorry. Oh, thank you. Yeah, you should be confused. That was wrong. Okay. Yes, let's try not to be... Let's just try to keep our confusion in the necessary direction, yeah.
So then the entire Jordan basis for this matrix A would just be E1 to E7.
Indeed. Yeah, the standard basis is always a Jordan basis if the matrix is in Jordan form.
Okay.
Yeah. Now, this doesn't really answer your question yet, though. Okay, so the theorem is this, is if T has split P of x equal to, well, in the language of Dummett and Foote, characteristic T of x, right? The determinant of x minus t, yeah? So if the characteristic polynomial is split, in other words, that's just a fancy way of saying that the linear transformation has all of its eigenvalues, right? So if t it has a split characteristic polynomial, in other words, there exists lambda 1, lambda 2, lambda s, distinct eigenvalues, right? And P of x is in fact equal to x minus lambda 1 m1, x minus lambda 2 m2, x minus lambda sub s m sub s, right? That would be what I mean by it's split. You can factor it into linear factors, possibly repeated. Then the big theorem here actually is that the vector space V is the direct sum decomposition of generalized eigenspaces. The generalized eigenspaces being, so K1, direct sum K2, direct sum, direct sum K sub s, where, K sub j is a set, has generalized eigenvectors, I can't spell, with eigenvalue lambda sub j. Yeah. The matrix is diagonalizable if and only if all of those generalized eigenspaces are eigenspaces. If all of those generalized eigenspaces are eigenspaces, that means the minimal polynomial is split as well. But it's the minimal polynomial is a product of linear factors, not repeated. So this is the theorem. So basically what you do, going back to your question, how do you calculate the Jordan form? All right?
Jordan basis.
Yeah, but to calculate the Jordan basis is to calculate Jordan form. So here's basically the algorithm. Number one, and it kind of always goes back to this, but calculate P of x and factor it. In other words, what you need to do is, find your distinct eigenvalues. All right, you find the distinct eigenvalues. And then 2, for each lambda sub j, part A, you find, right, what you got to do is you got to look at t minus lambda sub j to the power, let's say, p sub j, which is equal to 0, but t minus lambda sub j to the p sub j minus 1 is not equal to 0.
Where T is the original transformation
Yeah.
matrix that we have.
It's the original transformation.
What do you mean? The eigenvalue of what? Lambda I? That's trivial, but
Lambda, I'm using this for the jth eigenvalue. You could do it for the ith eigenvalue if you wanted, sure. But if these conditions are met, what that means is that there exists, right? This means there exists a generalized eigenvector of order p sub j with eigenvalue lambda j, right? Now that when I say that, I'm saying it's a vector such that, so this means that you can pick a vector x, I guess continuing in my litany of unnecessary jing. So you can pick an x such that this is equal to 0, right? But this is not. All right. And I guess I mean, I've gotten so many sub j's already, so let's just keep with it. All right.
You're just finding the degree for which the matrix T minus lambda is nilpotent, right?
Yeah.
That's it.
Right, the degree of nilpotency, right. And so once I do that, then I say this thing is equal to x sub j minus 1, and I'm off and running. Yep.
Are you guaranteed that the mass lambda and P sub j will be 0? For some, if you look at the A.
Yes,
the example,
I am guaranteed that it will be 0 for some power after I know, I mean, if it's a factor, that means that there's x minus lambda sub j to the m sub j in the characteristic polynomial, and then by the Cayley-Hamilton theorem, I mean, yeah, I have theorems which say that it has to be 0 by the time you get to the power m sub j.
wouldn't you need some factors for the other eigenvalues?
No. Oh,
Because, for example, for that,
yeah, you're right. Dang it. How to say this? Curses.
like, I mean, don't we know that it'll go up to m? Like, once you get to m, then any more than that won't work. So, let's see.
Now I'm stuck. I'm probably out of time to. That's not 15 minutes left. That's good. Let's see.
What you wanted to
Oh yeah, it's course
evaluations.
evaluations. That's right. But I brought cookies. I brought cookies.
He was talking about it first.
I-
He brought
I-
it up first. The cookies.
I brought the cookies. Yeah, but the cookies are unrelated to course evaluations. We discussed this already. Yeah. Okay. Point taken. I need to think harder about the algorithm. It's something like this, though. I mean, you find sort of your maximal weight generalized eigenvector, and then once you find it, you generate the chain. See, once I find E3 there, it like generates E2 and E1. Once I find the E6 or the 1, 2, 3, 4, E5 or the E7, it generates the E6 or the E4. And so once you find like the highest weight eigenvectors, then you generate a chain. And then you just go looking for the next highest weight and you generate a chain from that. And you just keep getting smaller and smaller length chains until eventually you fill out the whole WJ generalized eigenspace. And then you go on to the next eigenvalue.
And then the set of all the changes, the basis.
Yeah, the set of all chains will give you a Jordan basis, which means that but admittedly, there's something technical I'm forgetting here. Now, so this is very limiting though, right? Because, Celia, if I have this matrix, cosine theta minus sine theta, sine theta, cosine theta, well, this does not have a Jordan form, all right? Because the eigenvalues for this are lambda is equal to e to the plus or minus I theta, so short of theta being a multiple of pi, you can't find, it doesn't have the eigenvalues. It's not split linear. The characteristic polynomial for this, right, doesn't work. But good news, this is the quintessential real Jordan block. So like the real Jordan form says that even though you can take T, replace it with its complexification, right? And so the complexification is over the complex numbers. Good news, for the complexification, you can find the Jordan form. And then when you go back to the real, you get these like little 2 by 2 blocks. So like a good example of real Jordan form would be something like this. 3, sorry, Lorenzo, I'm almost done. -2, 3, but I respect you going mostly. Let's see here, 0, 1, 3, 2, -2, 3. So this would be an example of a matrix in real Jordan form. So what this would come from, this would be coming from the complexification having, so the corresponding complex matrix might be something like 3 plus 2i, 3 plus 2i, 1, 3 minus 2i, 1, 3 minus 2i. So this would be for a linear transformation which has eigenvalues. It doesn't have real eigenvalues. You'd have T on a 4-dimensional space that has complex eigenvalues, 3 plus or minus 2i repeated. And actually you have a pair of generalized complex eigenvectors. Those, when you translate back by the standard theorem, give you this, which is the so-called real Jordan form. It's the next best thing to diagonalizability for a real transformation when you don't have a full set of eigenvalues. You have complex eigenvalues. You can always do this, because we can always take a linear transformation, look at its complexification. The complexifications over the complex numbers, fundamental theorem of algebra splits the characteristic polynomial in all cases. Find the Jordan form for this. And then what you do is you take the Jordan basis and you rip off its real and imaginary parts, and they give you this, like that. And these blocks correspond to rotations and dilations in particular planes. So, yeah.
Since that matrix that is the rotational matrix, and the whole point of the eigenvalues is having like a linear transformation such that it's kind of like a scalar multiple. Like when you plug in the vector, you get a scalar multiple. So is that saying that since we can't find like the eigenvalues and there's like no like real Jordan form for when we're not in the complex, does that mean when we take it to the complex there is such vectors?
There is
so we plug in a scalar multiple when we rotate them?
Yeah. Yeah, I mean, in the complex case, there's always a Jordan form, because in the complex, the characteristic polynomial splits. Now, geometrically, like, what does this upward block of 1s mean in terms of real geometry? I don't have a good sense of that. Just like I don't have an entirely good sense of what this means either in terms of real geometry. What does this transformation mean? If I take x, y, and I multiply it by this 2 by 2 block, right? I know that it's just scaling E1 by a factor of 3. But what's it doing to E2? It's doing x plus 3 times. It's some sort of like skew. I don't know what it is geometrically. I mean, I know this is a 2 by 2 Jordan block. And by the way, once I know these things, I can show you how to solve. So you put these two things together, it gives you the tools that you need to solve any differential equation of the form dx dt equals to ax. So, have you ever seen that? What are your life plans?
Teach high school math.
Teach high school math. The question is, should I show you what else we can do with this next time? I guess I probably shouldn't. Now I'm starting to depart from abstract algebra 2. Yeah, we'll regret it. If I do, then I'll be tested to test you on it, and then that's just not a good place for us to be. This should be enough. Do you understand what the Jordan form is better now, at least? I mean, I could do more examples, obviously, but...
You have notes in like your linear notes, I think, on that, though.
Yeah, I do. I have a lot of notes on this. So next time, I'm going to jump over to chapter 18 and start into the group representation stuff, which will seem infinitely easier at this point, because we'll be at the start of it, not at the end of it. Now, the other thing, of course, is I still owe Daniel, and all of you really, a good example about Smith normal form and like reducing a matrix and finding the canonical form, rational canonical form using the Smith normal matrix stuff. And I haven't had a chance to work it out, but I do mean to do that. When I finally get to it, I'll post a video of it. It's going to take me a while. I think in the process of writing up solutions to your homework, I'm hopeful that it'll kind of give me an idea. And I still owe you a problem on your test, yeah? No?
You said the problem was irreparable, even if we turn the test back in with the test variables. You think about problem number 9? Or?
Oh, no. Number 9. Oh, by the way, I just posted the I found it. I found the missing page 9, missing problem page for number 9 that cost me an hour of my life to make up, and it's now posted. You can see it in all of its glory. Why it was totally unreasonable to ask you number 9, which is why I don't feel bad giving you a bunch of bonus points. Really, they're not bonus points, but regular points for redoing those 2 problems on the test, yeah? When's that due?
The exam?
Day before the exam? Oh, you're trying to make